Transitions are allowed when the integral overlap between initial and final orbitals is non-zero, which depends on the relative phase and symmetry of those orbitals. Think of atomic orbitals like waves that can be positive or negative, and when two waves overlap, their signs must line up so the overlap does not cancel out. If the positive parts overlap positive parts and negative parts overlap negative parts, the integral is non-zero and the transition is allowed. Spectroscopy selection rules come from symmetry and conservation laws that tell you which overlaps are zero by symmetry. For example, if an orbital changes sign under a symmetry operation while the other does not, their product is antisymmetric and integrates to zero. Light interacts through an operator, usually the electric dipole operator, and you check whether the product of the initial orbital, the operator, and the final orbital contains the totally symmetric representation. If it does, the transition can be observed. So, phase patterns and how orbitals transform under symmetry operations directly determine whether the overlap integral vanishes or not. A common mistake is thinking visual overlap alone guarantees a transition, because nodal sign matters and opposite signs can cancel out even when lobes appear to touch. Check the phase signs. Another error is ignoring the role of the transition operator. Assuming any non-zero overlap of orbitals is enough, instead include the operator when evaluating the symmetry product. A third pitfall is forgetting molecular symmetry labels and selection rules. So work through the symmetry table or use character tables to be sure a product contains the totally symmetric representation. For more videos and resources on how orbital phase and symmetry control spectroscopy selection rules, visit www.gumballdegree.com.